All right, here we go, talking about rotational motion. This is the first part of our rotational unit, and we're starting with the concept of torques. So let's begin with our definition of what a torque is. A torque is any force that could cause an object to rotate. Any force that could cause an object to rotate, that's how we define torque for this class. The reason I put could in there is because you can apply torques to an object and it doesn't rotate. Like if you applied torques in different directions, cause the object to stay motionless, not moving, they still technically count as torques. The object doesn't have to be rotating for it to be a torque. It just could. It just has to have the ability to rotate in order for us to call it a torque. Okay? So that's what our definition of a torque is. Now, just like forces, before we start talking about calculations and an equation and stuff like that, we're going to start by talking about free body diagrams. We're going to discuss how we draw free body diagrams for rotating objects. The first thing that's really important when it comes to these FBDs is that we have to draw the vector at the location the force is applied, which means that whenever we draw FBDs, we're going to have to draw out the whole object. So rather than when we drew FBDs, we were able to just like, oh, here's a dot, it's got like an applied force and a normal force, blah, blah, blah. But no longer can we do that for rotational. We have to draw out the whole object. So what I've done here is I've drawn out a meter stick, and that is going to be our first object that we draw this free body diagram for its rotation. Now, we did a lab last week where we were applying different forces to meter sticks. And the way we were applying that force is we were just plopping a mass on top of the meter stick. So in order to represent that, I would draw an arrow pointing down representing the force of gravity from the mass. Okay, and I've drawn it at the position where the object actually was, where the force actually was being applied. Another important thing we have to denote for our free body diagrams is we have to denote what we call the pivot point. That right there, that is the pivot point. That is the point at which the rotation originates from. Essentially, when this thing starts rotating, everything is going to be rotating around that singular point. Okay? So, next thing we'll do is we'll add, well, there was another force we applied, right? There was another force we applied, and it was over here. We had a little force sensor that we placed over here, and we applied the force pointing that way. So we'll call that an applied force. So we had two forces pushing down on this object. An important thing to note when talking about torques is direction. You see, when we were living in a linear world, it was pretty easy, right? Positive was up or to the right, negative was down to the left, most of the time, not always, but most of the time. Here, the directions, yes, there's a positive and a negative, but I think it's easier to talk about the object in terms of the directions of clockwise and counterclockwise, right? So if we look at this force right here, the force of gravity from this object, if, ignoring the force on the left there, if it was just this force of gravity acting on the object, it would cause the object to rotate clockwise, right? It would go in this direction. But if we were to say just focus on the force on the left here, just focus on this force here, then if we ignore the force of gravity on the right, it would rotate counterclockwise. Okay, so here's another example of why it's important to draw the vector at the location the force is applied, because both of these vectors that we see on the page are both pointing down, right? They're both pointing down, but this one causes the object to rotate one direction, clockwise, and this one causes it to rotate the other direction, counterclockwise. That's why it's important we draw out the whole thing. That's why it's important we draw out the vector at the location the force is applied at. But luckily, in the lab that we did, we applied forces balanced across the meter stick and put this object in a state called static equilibrium. This is a state in which all torques pushing the object clockwise are equal to all the torques pushing the object counterclockwise. I usually like to take these and turn them into mathematic equations. So basically what I'm saying is that all of the torques, by the way, we represent torque using this Greek letter tau. It's kind of like a fancy T. So I sum up all the torques pushing clockwise, and that is going to be equal to all the torques summed up which are pushing counterclockwise. Okay, now I think it's time for us to talk about an equation. Looking at our data from that lab where we had the meter stick and the masses and we're trying to keep it all balanced, we noticed that the distance the mass was from the pivot point increased the amount of force on the other side linearly, meaning that there is a direct relationship, they're directly proportional. Torque, or the force that's causing the object to not rotate on the other side, is directly proportional to the distance the other force was from the pivot point. Also directly proportional was the amount of force we applied. We increased the amount of force on the one side by increasing the amount of mass on that side. We saw that it linearly increased how much our force sensor was reading on the other side. So there you go. That is our equation for torque. Let's use it. Let's use it in a practice problem here. So I've got a meter stick here, pivot point directly in the center. I've got 3 masses attached to this meter stick. Mass 1, which has a mass of 2 kilograms. Mass 2, which has a mass of 0.75 kilograms. And mass 3, but we don't know the mass of mass 3. We're actually going to find it out. What we do know is that this object is currently in static equilibrium. It's perfectly balanced out. So we're going to use that to calculate the mass of mass 3. Check it out. I'm going to start here. All of the torques pushing clockwise are equal to all of the torques pushing counterclockwise. So which torques are pushing clockwise? Well, in this case, it's just going to be mass 3 over here. Okay? So the torque from 3 equals the torque from 1 plus the torque from 2. All right, I can start filling in information now. Let's see. Well, we know the equation is R, this distance here, which, by the way, forgot to mention back here, that R, we have a special name for that R. A lot of times we refer to that R as what's called the lever arm. That is the lever arm, is what we call that. So just keep that in mind as we move ahead here. So we have the lever arm of object 3 times the mass of object 3 times gravity. I chose mass times gravity because that's, the equation for force of gravity, and that is the force that is applying a torque to our meter stick. Okay? On the other side, we have the lever arm of object 1, the mass of object 1 times g, plus the lever arm of object 2, the mass of object 2 times g. Okay. Well, off the bat, I notice these go away. That's kind of nice. Now I can actually start plugging in numbers. So we have the lever arm of 3 was 0.5. We don't know the mass of 3. That's what we're trying to solve. Lever arm of 1, well, let's look back at the picture. It's not going to be just 0.15, right? Because remember, the lever arm is the distance from the pivot. The lever arm is the distance from the pivot point, so I don't need just that. I need this whole thing, meaning that our lever arm over here is going to be 0.45 times the mass of object 1 is 2, plus object 2 has a lever arm of 0.3 times its mass, which is 0.75. Okay, I plug this all into my calculator. I solve, come up with an answer that the mass of mass 3 is actually 2.25 kilograms. Okay, cool. Not too bad. Let's look back here and complicate things just a little bit. Let's take the pivot point, and what if I didn't want to rotate it here, but I wanted to rotate it from over here? Change where the pivot point is. Now, not a ton changes. The length of our lever arms are going to change, but also what's going to be important at this point is that actually the force of gravity that is acting on the meter stick itself is going to come into play. right? If you stripped away all of those other masses and just held a meter stick over here by the end of it, it would just naturally rotate. Why? Because gravity is pulling down on it. It's got a force of gravity pulling down on it. Now, when we consider that force of gravity in terms of calculating for torque, we're always going to essentially pretend that the force of gravity is all acting exclusively at the center of mass of the object, okay? So we're going to use that as an additional torque in this next problem. So let's say that the meter stick has a mass of 0.5 kilograms. And let's say I want to find the net torque acting on this object. I want to find the net torque acting on this object. So I got to consider what are all the torques acting on this object. I know that they're all pointing the same direction because they're all on the left-hand side here of the pivot point. So we have the torques will be torque from object 1, torque from object 2, torque from object, well, torque from the center of mass, right? Now notice I didn't put object 3 on that list because, well, its lever arm is 0, right? It's right at the pivot point. Its lever arm is going to be 0, so it is going to apply 0 torque to the system. Okay, let's start solving here. We have lever arm, mass, gravity, lever arm, mass, gravity, lever arm, mass, gravity. Okay, lever arm of object 1, looking back at our picture, ooh, it's a long one. It's all the way over there. So it's actually going to be all those numbers added together for 0.95. We know the mass of object 1 is 2 times 9.8 plus, this one has a lever arm of 0.8 times 0.75 times 9.8. Finally, we have lever arm is 0.5, mass is 0.5 times 9.8. Plug all those numbers into your calculator, come up with an answer of about 26.95. Hey, I forgot to mention what the units for torque are. The units for torque, well, take a second, look at the equation. Torque equals lever arm times force, so we have meters and newtons. Well, the units are Newton meters. Simple as that. Okay, so there you go. That was our practice problem. We got one last bit to talk about. What happens when there is a force at an angle? Can that still cause a torque? Well, check this out. Whenever we have a force at an angle, what we always did before was we split it into its parts, right? Into its vector components, where there was an x and a y component. Look at that x component, though. It's just pointing directly away from the pivot point. You can try this. Find a door maybe near you or something like that, maybe a cabinet door. Try and just pull away from the hinges on that door. What happens when you pull away from the hinges? Well, it's certainly not rotating, right? You're not going to get it to rotate like that. You have a better chance of ripping it off of its hinges than getting it to rotate. So what I'm saying is that really it's just going to be that y component that is causing our object to rotate. So I'm going to say this about torques. We only care about the part of the force which is perpendicular to the lever arm. In this case, that is going to be our y component here. We only care about the part of the force which is perpendicular to the lever arm. So with that being said, I'm actually going to go back, way back to our equation here. I'm going to add one thing, and I'm going to add a sine theta to the end there. By adding that sine theta, I'm essentially forcing myself to always calculate just the perpendicular part of the lever arm. Kind of just makes my job easier, really. So this will always cause me to get the y component of the force, and that way I know that is what's actually going to be applying a torque to our object. Okay, there you go. That wraps us up for torques. Hope this was helpful. See you later.